All right. Good day, everyone. Welcome to today's live stream. We're going to be discussing quantum computation. And we have Nick here, who's a research fellow at the Institute, James. And there's some interesting new intuitions that Nick mentioned we would like to explore. And that's kind of the idea of today's stream. The type of stream is an explore and learn. So we're going to be exploring and learning together in real time on this live stream. So yes, thanks Nick for joining us, and maybe you can just give us a bit of an introduction of what kind of ideas you would like to get into today.
Well, I don't have like anything specific. I wanted just to go through the current state of the framework, maybe mention some of the things I've been doing recently. I just posted yesterday, I posted a community post on the Wolfram community blog site.
Okay.
It's just basically short. Let me just give it a link. Let me paste it.
Cool.
I'm gonna paste it on YouTube, right?
Yeah, sure. You can paste it in the YouTube chat. The framework you're referring to there is the quantum framework, which is is it a packlet in the Wolfram language that you've been coding up for us?
It is a packlet, yeah, or sometimes it's just called a package, but in Wolfram ecosystem is usually called a packlet. We even have like a packlet repository, so it's there. I guess I can also should post a link to the packlet itself.
And the idea is what to be able to model and compute quantum circuits, which is using quantum computation, or just any kind of quantum circuits, even for theoretical physics.
It is trying to be as most general as possible. That's like what differentiates it from the usual other kind of like libraries people have in Python mostly when they trying to chase like actual hardware and like doing some real software engineering and over engineering it so that it's like very well fit for the quantum like hardware. So it's all about qubits, right? It's like some of the, you can say, like natural operations you can do on the quantum state, like resetting it to the other state. It's like usually called it's not even an operator. It's not a gate. It's like some kind of instruction, right? And we trying to like what I'm trying to do within the framework is like unify it, like somehow. And that's what mostly this post is about. Is like this special way of thinking about operators, how you can mix them together. So it's like a very natural mathematical way of like mixing operators in the quantum framework. In the quantum paradigm, you can mix operators, not just states, and you can use them very naturally to do some kind of operations like tracing out qubits and resetting them, and do some measurements automatically, discarding the environment and all that, and even like more.
So this is actually quite cutting edge in terms of the ability of what this framework can do. This is not. It's like quite new in abilities in terms of what software can even do at the moment. So you mentioned some Python packages, and they're not generalized enough to reason at the level of what this quantum framework is actually doing.
Yeah.
Wow,
yeah.
That's impressive.
So it's like, as I said, I'm trying to chase mathematics and science instead of the software engineering about hardware, the current state of the quantum hardware that is just built on top of qubits or some other kind of paradigms of computing.
Very
But
cool.
we can also, but we also try and do that too. So we're trying to like integrate some of the Wolfram capabilities into like other systems.
Wow. So there's actually a hardware implementation.
Send the circuit to the hardware, yeah. So you can still compile the circuit if it's like not as general as it can be, but also like only involves qubits. You can still compile to the standard libraries and also send them to hardware.
Okay, so help me understand something. So there's like quantum computation, which has a hardware angle to it in terms of quantum computers and actually trying to like see if it's possible to have like a quantum advantage with a quantum computer. And then there's things like Bell's inequality and like Bell's game and that sort of thing, where you're just trying to reason about quantum entanglement per se. And then
Uh-huh.
with the quantum framework, I've seen that you've actually created a notebook that simulates the Bell's inequality, or Bell's theorem. So that's pretty cool.
Yeah.
So you can actually like code up this stuff. You can run the experiment computationally, and then you can also have it have implementations in hardware. So that's quite powerful.
Yeah. Like, let me just start sharing something. Maybe we just should go and live stream some of it. Yeah, we're trying to design the framework like so that it's the most straightforward way. So it's not just about like some quantum algorithms, but also some quantum foundations, so that all the confusion about quantum theory itself becomes more natural if you explain it using like some circuits and diagrams. And basic like hierarchical objects and abstractions of our framework can explain it more easily because you can call them up. So it's like at your fingertips, you can take those objects and compute with them. It's much more straightforward. If computer knows how to do it, then a person should be able to understand it too, right?
That's actually a very profound idea. It's like kind of saying that in using a computer these days, you don't have to worry about what's happening at the assembly level and the instruction set data. So if you can have code that interacts with these quantum ideas, you don't have to go too deep down to start getting a feel of what the advantage of doing things in a quantum way could be.
Yeah, so it's like this example you mentioned about Bell inequalities, or the most modern version is those CHSH inequalities. They just like we have just a version of it as a single circuit, so that you can like just look at the components and run it like with a single line, get the probabilities, right? And you can do some computation on top of it and actually compute the properties, like what is actually being violated, what kind of inequality. But that's like the circuit that represents it.
Very cool.
And they're trying to build like a bunch of them. We have like so many built-in circuits right now.
Wow.
It's like this is like most interesting. That this one is represents the spatial entanglement, essentially, the spatial version, but it's also like time-like entanglement version of the same thing, of the Bell inequalities, which is like looks kind of the same. I've tried to do it to make it like look the same. So it's like the same kind of parties involved. You're familiar Alice and Bob, that are always a part of those kind of algorithms and protocols, right? So that instead of like having like 4 qubits, you have the same measurement to the same wire, and it's like you can extract the same kind of properties and entanglement of this kind of system. But it's like
the exact same properties or similar? It's not. Is there any fundamental
very
difference?
similar. You can very similar. I also had some post about this specific circuit. Right, so I explained it there, but you can extract the same kind of inequality of like if you set up the game of Alice and Bob, like playing the game of like throwing coins, that Charlie sets those coins up, and Alice and Bob trying to win some kind of game.
And these are entangled
right?
coins, right?
Well, the coins that Charlie throws are not entangled. It's like you can see that there's no connection between those coins. Right? Either here is just the classical coins, basically. It's represented by quantum states, but they're just probabilities, like 50 by 50, a fair coin. But what Alice and Bob have, they have this like bell pair.
Information
like
to share.
Basically, is that entanglement pair that they can share, so that they can, when they measure this, their corresponding part of that bell pair, they can extract the information about those coins and correlate their answers in such a way that like no classical counterpart can do. So they can win more frequently than the classical version without the bell pair. Or if you replace the bell pair with some classical log of like the maybe prepared experiments that you can just like go through and determine what would their answer be, what kind of measurement should they perform. This kind of setups.
Very cool.
So I guess I was trying to do I was going to go through like, instead of this high level explanation of protocols, I just wanted to go ground up.
Yeah, let's do that. Yeah.
Yes, like from the basics, what's quantum computation is all about, how do you represent all the abstractions and objects of the quantum world in our framework.
Can we go
So
at 125 zoom or 150 maybe on this notebook?
oh yeah, sure. Let's do 150.
Great. Okay, cool.
All right. So I think like the most basic thing people encounter when they just started to learn quantum computation is just quantum states, right?
Mm.
But I want to even go beyond that, below that, before even introducing quantum states. There's actually something more, something else you should understand about quantum things. It's the quantum basis. It's like it's basically how you represent all the amplitudes. It's like amplitudes in the quantum world is like coordinates and special relativity. It's like it's your reference frame. So you have to specify which basis you represent your amplitudes in, which then turn out to be probabilities when you measure them. So quantum basis is the object that tries to represent all possible reference frames in this quantum systems. But it's instead it's called quantum basis. We also have like a bunch of them, all the known ones. Maybe not all of them yet, but it's like expanding
So
very
is a
often.
basis like a type of amplitude? Does it have some kind of flavor depending on which one? Like why is it important to choose different ones? Okay.
Let me show you what the quantum basis is. I actually want to show you a little bit what's just the raw qubit basis. Qubit basis even raw is like a smaller version of the quantum basis. What I mean is that it has the same kind of types, right? What's like built maybe for the computational is the most standard basis in the quantum computation. It's a quantum computation because it's like looks like a diagonal matrix. And what it is it means that it has a bunch of representations. What is the representation? It's just I do the normal all that. Representation is basically okay, what actual the vector corresponding to each of those kets. All right, kets this is like a name of this particular basis. So you should think like this is the 0 ket and 1 ket. This is just like an index of the qubit because it's just a single qubit, right? So basically, a qubit basis is all it has is just this list of representations where it assigns to all the qubit names of that particular basis some vector representation. So this is like vector corresponding to the 0 ket. This vector corresponds to the 1 ket, right? So that's all basically what qubit basis has.
And is it one indexed? I'm just curious why it's a 1, not a 0.
Yes, it's one index,
okay.
Which is like very common way of. No, that's how Mathematica does it.
Okay.
How Wolfram language do. Every array is one indexed.
Okay.
So just to compare, like if we have a different kind of basis, like this Pauli X basis, it usually has some different names, right? Some conventional names like plus and minus. That's like the eigenvalues plus minus, plus 1 minus 1, and some different kind of vectors. Right? If you have more of them stuck together, let's do xy. Now you'll see that there's like representations for the second qubit. So the y now also has the same kind of representation, some kind of vector, but now it's their second index and also has some names. So that's how like the basic structure, you can represent every basis with this kind of object.
So is that ket, can you call that ket a qubit, or is it the combination of those kets which makes a qubit?
Well, this ket itself is just a name, it's like a label, and usually quantum computation, by themselves, they just label, you can call them whatever you want, right? Usually what matters if you actually want to perform some computation is the actual vector underneath it.
Okay.
And that's like you can think of the qubit basis just the storage of representation. Okay, this is the name, this is the label of this quantum state, basis state in this case, and this is what is the vector that corresponds to that name. All right. The quantum basis is a little bit more than just the qubit basis. It's just another abstraction of top of the qubit basis that you can use in order to actually assign these representations to some states and operators. Because you can see like any operator, any state in this diagram has an input and an output, right? And maybe potentially some other information. So quantum basis is like this holder of all this information and two qubit bases corresponding to the input and to the output of whatever object in the quantum computation you want to represent. So it has the same kind of name, construction that you can do. But now you can show the traditional form. It kind of has the same kind of representations as above, right?
Mm-hmm.
Maybe looking nicer, but it also contains like, for example, you can see that it has a nicer summary box. It has some picture assigned to it, which is not very important. Some dimensions, how many qubit, and also because there's like a line here, it shows, and there are list of 2 qubits. It basically counts how many output qubits and how many input qubits. For example, you can make this kind of basis that would correspond to some kind of operator with both input and output. For example, you want the basis that has an output of X and input as Z, right? Now it's for example, names will have brass in there, not just cats, right? So like this is the input, this is the output, right? Output goes first because the convention is the same as for matrix indices. You basically enumerate rows before columns.
Okay.
And that's why your output goes first. That's the convention.
Okay.
Right? So this is like how an operator with both input and output is represented as a quantum basis. Right? So the quantum basis is just this information about coordinates of your quantum objects.
So is
right?
the
Now
objects the operators, or the objects like the measurement points in your circuit?
Let me show you. Like the next kind of level in abstraction you have to create is the quantum state, right? Okay, we know the quantum basis. Now that assigns all those vectors to all the quantum labels, right? But we don't have yet a way to actually weight them with some amplitudes. Okay, so that's what the quantum states comes in. When the quantum states comes in, so now we have a quantum state. It's like the most basic one is like 0. It's like just the 0 cat. But what it actually has is just this list of amplitudes, essentially, right? That you assign to each of those names in the computational basis over here, right? So it has a 0 cat label, 1 cat label, and you just assign a list of amplitudes to all of those labels. And that's what quantum state is.
It's a probability, or is that the right way to think about it?
No, those are complex amplitudes usually.
Okay.
Right? So you can, if you do the random pure, right? So random pure state is just a list of random complex amplitudes. So this is like a complex amplitude assigned to label 0. This one is assigned to the label 1. Right? If you actually want the probabilities, you should do. I think I'm gonna use some random state often. Let's just fix one so that we can refer to it later, right? So if you have amplitudes, if you want to extract the probabilities, you take the absolute value and square it, right? Or you just ask for probabilities directly.
Okay.
So that's the quantum state.
So the state contains these quantum amplitudes.
Yeah, so it's easy to see, for example, like a Wolfram language has like all the expression has some corresponding, all the object or whatever has a corresponding expression underneath. It can be formatted nicely as some kind of summary box, but underneath there's some kind of raw expression, and we can just explore it. So the input form of this quantum state is just some sparse array of amplitudes, right? So it's just 2 amplitudes and the quantum basis that we just discussed. It's just like a pair of amplitudes and the quantum basis, which just knows what those amplitudes mean, like what are the names, what are the representations for those names and labels, like picture and all other information.
And then generally you would just fill that sparse array with random values.
Well, if you want the random state, then yes.
Okay.
But usually, like here, it's like there's some special state. Like this is the plus state, right? For example, in that circuit above is the quantum state plus, right? And plus has like this like uniform amplitudes over 0 and 1, so they're equal amplitudes for 0 and 1.
Okay. Got it.
Those are like the basic states that you usually encounter in quantum computation, like plus, minus, which is just the minus instead of plus, and all that.
Got it.
Maybe you can make a, for example, Bell state above is actually 2 qubits. Right now it's like the superposition. If you think of the 0 as spin up, is spin down, and 1 is spin up, this is a superposition, usual superposition that the Bell state has. And this is the same kind of state that, like in this diagram, is represented by this nice cup wire, bent wire. Actually, a nice way to make our own basis. You can actually come up with your own names, like if you actually want to do some spin basis, you do it like this. You just, by default, it's gonna be the computational one anyway. So you can make your own names, right? So it's gonna have the same kind of representation as the computational basis, but you change the names.
That's cool.
And now we can, for example, cast this quantum Bell state into these spaces. And now it has this more familiar representation and has a traditional form.
Very cool.
So that's one very convenient. You can even like make some cool stuff that I like to show. You can even use, I don't know, emojis. Like this
Yes.
dead cat, like alive and dead cat, whatever.
Okay, so that's Schrodinger's cat.
Yeah.
Is there a way to represent that as a matrix? Like, I guess it would be a complex matrix, so is it possible?
Well, actually, let's just go further. This reminds me what kind of other types of states you can create. Like we just created a state which is just like a vector list or list of amplitudes, right? So we just created a state represented by a list of amplitudes. But a more general way of representing a state is actually a density matrix, right? Which is like in the quantum parlance, it should be like positive, semi-definite Hilbert or Hermitian matrix, right? So for example, so basically instead of a list of amplitudes, it can be like any Hermitian matrix like that. Or you just it says a known state because it's like has some symbols in it, so it doesn't know whether it's a valid Hermitian one or not. But or you can just create a random one. So now it's a actual density matrix underneath. And also any state represented by a density matrix is what we call a mixed state in general. Okay.
So can we see that actual matrix? Is there a way to visualize what the matrix looks like?
You just extract the density matrix, right? Well, it's usually a sparse array, so do matrix form like that.
Okay.
There are different ways of representing states, of course. You rarely actually look at the matrix itself.
Yeah.
Like one way of cool visualization would be just because it's a two-dimensional state, which is the qubit, you can just look at its underlying block plot.
Yeah, that makes sense. Okay,
so just represented by the direction. So
and you can move that around. You can like.
Yeah, that's 3D. You can move this around. So it's like any random mixed state, because it's random every time I relate it, it's going to point it to a different direction. Because it's mixed and represented by a general density matrix, what distinguishes from the pure states that we had above that just had a list of amplitudes is that it's actually pointing to the bulk of this ball, of the sphere. While like if you make a pure, like we did above, and ask where it's pointing, it's always going to point exactly to the surface. So it's like has this maximum length. Or you can say it's like has purity 1, it has von Neumann entropy is equal to 0. So the pure state is basically the surface of the block sphere.
Wow.
And the mixed state is all its bulk, right? And obviously every point in the sphere represents the space of all the valid quantum states. You can even go backwards. Right? There's a special named quantum state that takes block vector and 3 random coordinates. So it's not going to as a list, right? So that's how like coordinates in this XYZ coordinates of the block vector in this picture, it's how they correspond to the actual amplitudes. Or I would say not the amplitude, or density matrix components. That's how they correspond to each other.
I see.
So maybe I should call them not ABC but X, Y, Z, because those are X, Y, Z. Right. So basically, a three-dimensional vector is the same as this 2x2 complex density matrix. So those are the same quantum states.
Very cool.
So, all right. So what's next? Right. Another common operation in the quantum computation is to take, like, this is the state with an output, so it's some kind of ket, right? If it's a 0, it's a ket vector, right? But how do you make a bra? It's usually, well, in the framework, you can just power it in this, assign this dagger, right? It's like a power dagger, basically turns the state into what it's called an effect. Why it's called an effect, maybe I'll comment on later, but that's basically the bra version of this ket state, right? So now you can think of it, while the quantum state has only the output, right? For example, if you like do the circuit diagram, which is just basically saying the same thing as putting it into a circuit like above, right? The dagger version, the bra version, is just gonna point backwards.
Okay.
Right. So it's like natural to ask, okay, if they have the wires there, can we connect them together? And sure, we can like make them into a circuit. For example, if this is the 0, 1 first, and you don't have to put the quantum states, you can do just the strings. You should be able to figure it out, right? It's gonna have like the actual labels so that we can connect together. And when you don't have, if your overall diagram doesn't have any inputs and outputs, but basically means that this diagram represents just a single number. So it's like a scalar, while like this was vectors, sometimes called like, this is contravariant vector, covariant vector, because it has some inputs and other has some outputs, so that you can like put index on top of or the bottom of your symbol when you actually write the math down. Or like in diagrammatic notation, it just means, okay, there's no free wires, then it's a scalar. And when you evaluate the circuit, if you evaluate the circuit, you get the scalar. So basically, you don't have any qubits anymore. It's just like a single dimensional thing, one-dimensional thing, which is just a single number. You can like, in this case, it's just one. This is like a, let's do it more interesting. Let's add plus here. Then there's like the some number, and this is like a name for the basis. So it's like one-dimensional basis has this weird scripted one. So this is the actual number that you get when you combine this together. Or you can, instead of do that, you can extract the scalar, just the scalar itself.
When you say evaluate, is that kind of like taking a measurement? Is that what you're doing?
No.
Okay.
What I mean is that whatever diagram you have, like all those states wired together, operators, you can actually, all of them represent some kind of tensor, right? It's either a vector, row vector, column vector, matrix, or arbitrary rank tensor with more wires, right? If you wire them together, it means basically you contract a bunch of tensors together to compute a new tensor. So it's like a neural network essentially.
Okay, so this representation or this specific quantum circuit, when evaluated or like brought into one tensor, actually just becomes a single number.
Yeah. So it's like before you evaluate it, it's just a bunch of tensors, but then when you evaluate it, you basically contract them, so you sum up the specific indices when they connect it with wire. And then depending if you have free indices, then it's going to be some rank tensor. If it has a single free wire in the diagram, it's going to be a vector. If there are two wires, it's going to be a matrix. Free wires, free rank tensor, and so on. Right. So that's kind of, for example, like this diagram above, it has, if you ignore the measurements for now, they have like 4 wires. So if I were evaluate this, I'll get basically a 4-rank tensor.
4-rank tensor. Okay.
Yeah. So which is just a state of 4 qubits in this case. You can still kind of flatten them out to present it as a 2 like 16-dimensional state vector, or you can just represent it by a tensor of 4 qubits, 2-dimensional qubits, 4 2-dimensional qubits. It's either 6-dimensional state or 4 2-dimensionals.
So is that the
Like
measurement outcomes there? There was 16, so that would be like a 16-dimensional.
Yeah, outcomes. Yeah.
Outcomes. Okay.
So this measurement for this particular circuit, there are 16 measurements because we are measuring 4 qubits.
Yeah.
Each qubit is 2-dimensional, so you have 4 to the power 4, 16 total outcomes.
Okay, so easy to understand so far.
Right, so we have these simple diagrams. I guess I can also show that what's going to happen if you switch the place around, right? Instead of actually contracting those vectors, like this represents just corresponds to just a simple dot product. It's like 2 vectors, you just dot product them together, you get a scalar. If you do it in the opposite way, so that there's like now 2 wires, that's the matrix. That's just a matrix. If you relate it, actually, you get the quantums. Now, that's because by default, when you evaluate it, it's kind of automatically pads some initial states. So actually, you need to turn it into a quantum operator, which I'm going to talk about next anyway.
Okay.
So if you turn this into a quantum operator, it contracts it and now has this object that's just which we're gonna talk about soon. It just it now has both inputs and outputs in general, and you can wire all these quantum operators together within the diagram, and you can put wires all over the place if you want. Okay, so we have quantum states, which can be states, effects, maps in general. So what distinguishes a quantum operator from all those different ways of having just amplitudes with a basis, right? So the quantum operator is just like basically a further level in this abstraction tower that we're trying to build here. It's a quantum state with some information about where the wire is going. That's essentially what all that is. You can even obviously there's like a bunch of built-in named operators that you already can just build explicit without any explicit coordinates of your matrix. You can just ask for some swap operator. It's basically arity2. It means it has 2 inputs, 2 outputs, which all of them are 2-dimensional. Has some cute diagram like this, right? But it's input form, like we've been looking at the quantum states, which were just a list of amplitudes and a quantum basis. We can do the similar thing for the quantum operator, and you will see that it's actually just a quantum state, which we already know all about, and some just information about the wires. And that's all it is. So it's just this quantum state is kind of represents more than just a state on effect. It's just in general a map. So if you look at the inside of this box, it kind of distinguishes what dimensions are the input and output, which is like this small little simple notation, so that you can distinguish whether you can actually split and separate outputs from the inputs. Okay, like just to comparison, if we had this 0 before or 0 0 state, it has no inputs because there's nothing to the right of this bar, this pipe symbol. If you compute the dagger, which just flips the cat to the bra, making an effect. Effect means just the other way around. There's nothing to the left of this pipe symbol. That's just a simple notation that the summary boxes have in order to distinguish the different types of quantum states.
Okay, so is this in a way you take it's a way to take one state, something happens, and then there's a new state, input state, output state.
It's not like something happens. It's just
okay.
You can think of it as like all of it is just some kind of tensor underneath, right? A tensor is just some arbitrary rank thing. So in both of those cases, it's the same. The tensor has the same shape, right? It's like 2, 2. It's just 2-rank tensor, but you have to distinguish for this diagrammatic purpose and how to actually compose those things together, which dimensions correspond to the input and which dimensions correspond to the output, right? That's what the basis, that's what is basis for. It serves this function to split this,
I see.
split the shape of the tensor into two things, covariant and covariant dimensions. It's like actually putting, if you do the tensor calculus, yeah, in usual math notation, you usually put your indices either on top or on the bottom of your like tensor label, right? Here you just you have a basis and you just say which qubit basis is the input and which one is the output. That's how you separate all the covariant or contrariant indices.
So the entire circuit is some big kind of tensor object or quantum state itself.
Exactly.
And then the operators are just saying like which values correspond to inputs that and outputs, something like that.
Yeah.
So what's actually being operated on? What is the actual operation? It's like given an input, there will be outputs, or is that still coming?
Well, so it's all tensor contraction.
Okay.
It's like I show you, every operation of actually computing new tensors from other tensors, like new quantum objects, quantum operators, quantum states from old ones, is just about putting them together and wiring corresponding indices and contracting them. It's like it's just all very complicated Einstein notation of a bunch of objects, right? But you present it instead of just a bunch of symbols with indices, you present it diagrammatically. Right? For example, let's just take this some other. Let's take a different circuit like this, right? And just for concreteness, to every circuit, from every circuit like that, with just a bunch of operators, you can see. Can ask for a list of operators. You see that there's a bunch of operators. They like have some different wires corresponding to them. Like this one acts on the second qubit, right? Like this one acts on the first one and the third one. We just put the picture together. That last one is the swap one. So that this is the swap. So this is the one that acts on the first and the third qubit, right? And to every circuit diagram like that, you can build a tensor network out of it, which is just a graph. It's just a graph where the vertices are those tensors, and the edges just show that okay, this two tensors that are incident to this edge has to be contracted somehow. There's some also information on what actual indices are contracted are hidden in the edge labels. You can actually show them. Automatic. Yeah, those are like a pair of indices that are being contracted. So it's like you don't have to worry about like what this actually means. You can see that there's also some nice notation to distinguish what are the contrariant and covariant indices, so that you can really see by the names of those indices that are being contracted, which is the input and which is the output. Right, so this is just some names of the gates and so on. So basically a tensor network is the object that you can compute from the diagram, where every vertex is annotated by some kind of tensor, and you can like take this net, and what is being done is just, I think I have this function that just takes this net. It all contains already all the information you need. So just when you contract all these individual tensors, you get another tensor, this like 3-rank tensor, which is the output of that, or what you get after evaluating this circuit. What the actual circuit that you've been evaluated here, because it has 3 inputs, 3 outputs, so you would think you get a 6-rank tensor, but actually there's some hidden automatic thing is happening. The actual circuit is being evaluated as this one. So you can always assume, in quantum computation, you always assume that that your circuits act on some registers, which is just a name for zero cats. So you act on this simple initial state, which is just a bunch of zeros.
Got it.
And when you evaluate it, you have three outputs. That's the tensor that you get after evaluating it.
Hmm.
All right. So I guess another thing I was wanting to show you actually about the quantum states.
Mhm.
Maybe you can like digress a little bit into quantum foundations and just
Yeah.
see some different representation of even the quantum states.
Yeah, sure.
So we just discussed that you can like build the states, which is either random pure vectors or arbitrary mixed one density matrices, right? So actually, let me show you instead how those mixed states are different. This is actually the content of my blog that I posted in the beginning. How would you make diagrams, the circuit diagrams, when instead of just simple vectors, you have states represented by a density matrix instead,
Mhm.
right? Just diagrammatically, they're already going to be different. You'll see that if you have a mixed state in this case, it's going to have this big border around it. That's how you visually differentiate between the mixed state, a density matrix, from the vector. So it's a matrix state, that's a vector state, right? So what's cool in the framework, because as I showed, there is like this nice abstraction level hierarchy that you can build from the basis to state to operator, right? It means that if an operator is just a state, and the state can be not just a vector but a matrix, right? That means that every operator also can be some kind of matrix state,
Mhm.
a matrix map, not just a state but a matrix map. So there are a few examples. Like this is the most basic matrix state that you can build. That's like usually people like that's what you usually label as your matrix state like that, right? So that's
Mhm.
your rho, which is the usual name for the density matrix. Another kind of object is also obviously if you just take the conjugate of that, right? So you can have mixed matrix states and matrix effects, and when you can also wire them together, that's going to correspond to some kind of dot product, inner product between matrices now. While before it was just a vector dot product, now it's have to be a little bit trickier. That's give you what is actually going to happen underneath. Maybe I should explain what's going to actually happen, right? Let me just show you what is actually happening when any circuit with matrix states or maps in it happens when you evaluate it, when you want to construct the tensors,
Mhm.
right? Because you kind of have to treat those matrix states some differently, right? And they treat it differently because when you actually try to evaluate this one, for example, what the actual circuit that's being evaluated is this one. I guess I forgot to remove some echoes from today, right? So what actually happens is all those matrix states are being flattened. So for example, if you had a matrix, this is like a qubit 2x2 density matrix. When you flatten it, you get a vector or four-dimensional vector. But with a four-dimensional vector, you can now draw across two qubits instead, right? And
Mm.
represent it as a vector state. So
Mm.
basically, you can that's process what I call bending. You basically bend this state into a vector. You bend a matrix state into a vector, right? So that now you can use an additional qubit or qubit wire to compute the whatever diagram you're computing, but without any matrix maps, matrix states within it, but only using vectors
Mm.
and just
Okay.
conventional tensors, right? And not like mixed in any way. So it's like that's what happens when you have a bunch of mixed states and effects in this case in the diagram. You flatten them out. Now it's like they have occupied one more qubit or twice the number of qubits in general, and you
Mhm.
contract the usual vectors. And that's going to be the corresponding operation that one's going to do when there are more complicated mixed circuits
Hmm.
are being evaluated. All right.
Okay.
Actually, okay. I know what's next.
Okay.
Right? So actually, there's a more abstraction tower we can build from beyond the quantum operators where we stopped.
Yeah, that's what I wanted to
actually
find out. Yeah, like
we haven't actually mentioned any measurement, right? Only like in passing in the beginning, right? So the next actual abstraction we should learn about an object is how to actually do the measurement. What does it mean to measure stuff? Okay, so the thing for that is the quantum measurement operator, right? So that's the next object in our tower of abstraction. And again, before we go further, let's just look at this input form again and just confirm that it's just nothing else that's just a quantum operator with some kind of list. What is this list? Is just a list of targets that you measure. So if you think of this simple abstraction tower, is just okay, if you want to measure stuff, you just need an operator and some information what the actual operator actually measures, right? So,
and
for example,
are those measurements like specific numbers in this big tensor, and then, or does it have to be only inputs, outputs? Can it be any point in the total combined tensor?
it's easy to see as an example. Like, as soon as you have measurements, you can represent it by this M letter, which is actually just the list of numbers that you want to measure. It's like this just says, okay, I want to measure the first qubit, the second, or whatever. Right?
Okay.
So for example, add some states, some measurements. Let's do it like this. Oh, that's an ugly thing.
Okay.
Let's do it like.
So there's specific things you can measure. There's yeah. Okay.
Yeah. So this is like builds a quantum measurement operator on a second qubit, right? And that additional information from the operator that quantum measurement operator contains is just a list of targets to indicate what the actual measurement or what the actual target qubits are.
Okay.
Right? Because it's important because it's not just the order. You would think that it's like enough to represent like an operator already contains the order of where it acts on, right? So in a way, it's not enough because you can also compose those measurements together. For example, if we want to measure the same qubit twice for some reason, right, one after another, you can compose them together to make a new measurement operator. Now its target has the same target twice, right? So we have the second qubit twice. So that's basically tells you that we measured it twice, but the input, even though the input order of the underlying operator is just the second qubit, right? So you kind of infer, you can see that. Let's actually expand this diagram a little bit and see what this actual measurement operator is doing. It's like you can already see from its order that it can create some kind of extra qubits. So it's like even though it has a single input, a single qubit, it has 3 qubits as an output. So it creates some extra qubits, and the qubits it creates usually like in the opposite negative direction. That's what this arrow is doing, right? It's trying to indicate is the direction of those extra qubits that quantum measurement is creating.
So are you saying qubits or qubits? Qubits?
Oh yes, I'm saying qubits in general because like it doesn't necessarily have to be a qubit. It's like arbitrary dimensional one.
Oh.
So that's why we usually just say qubits because qubits is just a special case.
Got it.
Like I haven't showed any examples, but you can make what would be an easy. Do we have like some natural way of creating one?
We can't use the cats.
Just 2, I wonder. Okay, if you specify the dimension and you have some strings here, like this would be like 4 qubits because they're 3-dimensional. It's like qubits. It's like a state 4 qubit state.
Okay, got it.
Yeah. Okay.
So just a quick question to recap my understanding here. So you can only measure qubits, which are quantum states in your quantum circuit.
Well, in the circuit, you kind of don't differentiate what you don't know what the state is. The state is just a wire. It doesn't matter where this wire is coming from. You could have created it with a state, but it's like, well, there could have been some operator acting on there, right? Some Hadamard. No, it's like I'm measuring whatever happens when you apply the Hadamard state, right? Or you can just remove this underlying states. It just represents whatever I put in here, or it's going to be measured, or overall circuit is just a type of measurement that can be applied to some state.
Got it.
So this circuit is actually operated. That's why our circuits are also an operator. It's just this decomposed version of operators, when instead of just a single tensor, and then if you have a bunch of them, and the information how they're wired together.
It's interesting the way you use those words, because that kind of ties into this concept of an observer, or like creating a measurement is an operation. There's no objective measurement you can do that's not actually operating on the thing you're measuring. But it's just interesting that the description of what's happening here actually relates to experiment in terms of what people are doing.
Yeah, we can like discuss the actual like explanation, semantics of what actually all this means. For now, we just focus on the actual mechanics and coding, or how those things are being computed without like assigning any meaning to what this measurement means in the lab and all that. But we can do it later.
The point here is that the measurements have to happen on the wires.
Yeah,
they're placed on the wires.
In this case, it's just very naturally. It's just some kind of another version of an operator. It's just another operator with some special semantics you assign to it that you interpret as a measurement. But it's just another tensor. In this case, it's a tensor that has, like by default, it has these two inputs, because we want to distinguish
outputs or inputs?
The false measurement.
You said inputs. Did you mean outputs?
No, outputs. Yeah, single input, two outputs.
Yeah.
So it's like it created this classical wire, but kind of it's not really classical, because it's still a quantum diagram. You can even act with some operators in there on the zero wire connector. But it's just another quantum operator that you can put in your diagram and perform computation.
Makes a lot of sense. That's cool.
All right. So if there are more measurements, like if you measure this guy, it they kind of put those wires in order. You've created them. So this was first, so it created the 0, 1. This was second, so it's created the -1, and create those things. In this negative direction.
So is this the whole idea of quantum computers? Is that you have to compose, you have to compose these circuits so that the measurements eventually constrain like the potential. Like you have to structure the operations in a specific way to actually form some sort of advantage from the quantum states. Otherwise, you would just use a classical.
No, I wouldn't say so. So this is, first of all, it's like this way of building circuits is purely like theoretical. That's what theory tells you the most natural thing to build or compose stuff together. Like this is like what we're essentially doing is a categorical quantum theory here, because those diagrams is just special ways of composing processes together and wire them. So this is like a representation, natural way, visual way of representing categorical quantum theory, right?
Okay.
What you actually do in the lab, and when do you have advantages, like all other like kind of worms, but yeah.
Okay.
Okay, so I want to show you. Let's just actually perform. Like when you actually measure this classical thing, I think by default it's not gonna return. Oh, it's actually, yeah. It's kind of, I think it's traced it out automatically. Oh, it's 4 outcomes. Yeah. Like this quantum measurement is actually like a second. It's an abstraction that comes after the measurement operator, but it's very simple. I guess it's explained it. It's okay. We measure. Let's not have this thing here. think it's confusing. And let's put some. We just put some simple circuit in here. This is a built-in circuit that constructs the bell pair.
Mm.
And we just measure it. So it's naturally, if you measure it, you should get the probability is 1/2 for every outcome that we had. It's like, but previously we had this bell state, right? And which is this just superposition of 2 spins down or 2 spins up. So they correlated with each other. So that corresponds to the measurement.
So that dotted line around bell is just like injection of a predefined circuit that doesn't represent anything special in terms of the quantum.
Yeah, that's right. We can like have arbitrary sub-circuits nested together.
Got
so
it.
like you could, if I put just list around these measurements, for example, I will just put them in this sub-circuit.
Okay.
And sub-circuits that doesn't even draw this wires from inside. So basically kind of just nest together these diagrams to make them nice, much more nicer.
I got it.
Like this is like another built-in circuit corresponding to the quantum Fourier transform, right? Just also a circuit.
You can connect all these predefined circuits up.
Yeah. So oops. This happens. There's some dynamics in those circuits. Sometimes I click on them and it crashes. Did I save it? Okay. Been saving. Hold on. Yeah, that happens. Okay. Can I reload it? All right. That's an Android thing. Okay. Don't click on this thing. Remember.
Okay.
Right. Okay, where was I?
Yeah. Hey memes, Carlos is at the airport right now, but he's listening in, so he's in the chat. It's just Nick and James today, and we're discussing quantum. What was that term that you mentioned earlier? Categorical quantum theory or categorical quantum computation?
Yeah, it's kind of related. I wouldn't draw too much distinction. I don't know, they're very distinct from each other. It's just about how you can formulate quantum theory in terms of just your usual categorical terms, objects, morphisms, and functors, and how there's like an underlying category behind that, like symmetric monoidal dagger category, like this dagger that we did on the quantum state here. That's the dagger in the name of the category. It's just describing that, okay, there are objects in the category that you can dagger, and you kind of have this dual object, right? And there are two types of it's monoidal because you can take tensor products. This is this vertical product, like here is a tensor product. Well, maybe like this is the tensor product between two states. It just means they are side by side together. And the horizontal composition in this case, in this running along the depth of the circuit, is the usual composition.
Oh, got it.
Right. Yeah. So that's just the way to formulate all of these nice diagrammatic pictures.
Got it. That's cool. Okay, so where are we on the power now? Where are we on the structure of this? Yeah.
So I can briefly explain like what this measurement, just for completeness, what's the underlying input form of this measurement, right? As we did for other objects, and actually very simple, because underneath is just the actual wraparound quantum measurement operator. It's like it doesn't have any new information. It's just a quantum measurement operator that doesn't have any inputs. So its measurement is just because it acted on a state, right? There's no new input wires. It just has a bunch of, there's no inputs, just the outputs. It's still kind of technically a measurement operator, and you can treat it like the one. most of the properties of this measurement operator directly translate to the measurement, whatever you want to do with the measurement, like extracting probabilities, post-measurement states, and all that.
Got it. Okay, so we were just creating the measurement operators before. You still need to make the actual measurement.
You don't make it. It's just a way of representing it.
Representing,
right? So because what you always make is just a bunch of tensors with numbers. It's just a matter of how you wrap them together and extract some useful properties from those tensors, right? So underneath, just remember, there's like a tower of abstraction here: quantum measurement operator, state, which does contain the actual numbers for this tensor basis that knows how to interpret those, right? With all the information. That's just you look inside of that and extract some useful properties, probabilities, states. There are some pictures, plots of probabilities, and all that.
And then at the most basic level, you have the qubit or the qubit, which is in reality some kind of entangled particle normally.
Yeah, well, if it's a multiple qubits, then they're entangled. A single qubit can be in superposition. It doesn't matter. It's just like an arrow on this block sphere. It's
so
like it depends on which basis
or whatever.
It basically, when you say that the quantum state is in superposition, it doesn't make any sense without specifying in which basis. Right?
Okay.
If you just pick the basis, it can be just this specific basis state.
Okay.
Right? Completely orthogonal to the other basis state of this basis.
Interesting.
Right. The entanglement is when you have at least two qubits. Actually, let me show you like this. The basic entangled state is the Bell state, right? We already seen a bunch of times. That's the quantum. That's the entangled state because you can't decompose it as a product of two states in superposition in whatever basis. Like you can't pick the basis for those individual qubits so that this state is just a product of those. Right, and you can quantify it like we have a bunch of properties named. Oh, I think it's not the distance, but entangled monotone. Have a bunch of built-in ways of measure the entanglement. Right, I think it's. Does the one means it's entangled? Should be. I'm kind of forgetting what it means. Let's try just, So for example, Rene entropy for the entangled state is 1, but for this state is just a product of 0 and 0, which is like non-correlating, non-entangled two qubits. Then the entropy, this entanglement entropy,
0
is 0.
That's so interesting. Wow, that's so cool. I like that.
Okay. Well,
okay.
Just that you can another way of computing this kind of metrics. It usually involves just tracing out one of the qubits. I haven't showed what the tracing out usually means. You like in the conventional parlance, when you trace out the qubit, it means you discard it. It's like you can trace out this measurement result. That means you trace it out, right? A partial trace, it's like computation. It means you just literally trace the part of your density matrix that corresponds to this system, right? For example, if this Bell state is a state of two qubits, you can trace one of them. There's a convenient function that traces. Like you can trace the first one. Usually you get the mixed state. Even though the Bell state itself is a vector state in superposition, entanglement superposition. When you trace it out, you get some mixed state. In this case, it's even like a classical mixture of just two states that like probability 50-50, you get 0, 1. And you get, and it doesn't matter which one you trace, you get the same state. This kind of state should be, that's like the middle of your block plot. That's the center. Like you don't even see, like this is the uniform mixture. It's like basically you have zero knowledge about the probabilities of that state if you ignore the second one. You have no, it's like it's either that one or another. That's the uniform mixture one. This is like very convenient state, right? This is what we call uniform mixture. It has a name, right? So you can kind of see that they're the same, but this signature plot of all the states, you can kind of without even looking at the amplitudes, you can just look at this little plot of the matrix, and by colors, if they match, you can see that they're the same. Right? It's usually already enough.
If they match in what way? Like one,
Well,
two
just
to
literally
one.
the same. So if those signatures are
Oh,
the same,
the signature.
then the states are the same. Right? So without looking like at the actual like traditional forms of those. If the states are big and there are many 2 qubits, it's very useful.
I'm trying to understand what the trace is specifically. Are you saying the trace is like one specific quantum, like the trace of one quantum wire or something like that? Is it one quantum circuit?
You can actually represent trace diagrammatically in a way. It's like without thinking too much what actually computed. But if you have a bunch of states here, right? Maybe let's do this uniform superposition. Oh, wow, we had the bell. So we have the bell. You can actually do this trace. I just recently added this new, fix this diagrammatic thing. Well, actually, I haven't fixed it. I need to fix it a little bit. It should look nicer.
Okay.
But yeah, like tracing, you can think of tracing as actually this discarding of the qubit, whatever you want, or whatever qubit you want to discard, right?
Okay. And why would you want to
And
discard the
discarding
qubit, just in terms of practical application?
there are many applications. Like if you have this measurement above, right? But because by default, you have this extra things created. You can maybe you want to actually trace them out, okay, and ignore the results of those measurements. Right now, you don't have to worry about them. Now, this wire represents the post-measurement state, whatever it is, and it's going to be like a classical thing. It's just going to be, oh, you would the right thing to say it is just the state decoherent. So it's like a mixed state with all diagonals 0. So it's like a classical mixture when you only have a density matrix with only diagonal terms. That's what's going to happen to this wire representing a post-measurement state when you actually trace this additional extra qubit that the measurement creates.
Interesting. Okay. So in other words, these quantum states can almost like propagate in certain types of circuits. So you want to diminish those quantum states just to simplify the entire circuit. Something like that.
Well, diminish it depends what kind of quantum operation or quantum algorithm you're trying to simulate, right? Because here it's just we're simulating, we're not doing actual experiments. We just want to represent our experiment in the laboratory in the most natural way possible. So we have this abstract like names for the operations that we want to perform, like tracing and discarding qubits. I can measuring them, but this means computation is just this kind of operation. This trace, by the way, is just this uniform mixture, or its dagger. So the trace is actually equivalent to the dagger of this completely mixed state, which is just in the middle of this block sphere. So this completely zero knowledge information state, but you're trying to apply this zero knowledge to your state. That's how you discard it.
That's interesting. So that has application, maybe not to just sidetrack too much into experimentation, but for example, when they try to do stuff like the quantum eraser experiment, where you deliberately destroy the information in order to not know what the outcome of an entangled particle pair might be before a certain time. I don't know. I'm just thinking that might be one example of where you want to destroy the information of a quantum state.
Well, I imagine there are some applications. Yes, I just not know. I'm also like developed this intuition about like all those tracing diagrammatic versions of them, that they are actually just the mixed versions of this quantum maps just recently. That's why I wrote this post, right? That's and try to compose all different applications of those. And since then, since yesterday, I already had a new application.
Right.
Right. So I listed a bunch of them. Like this, I talked about this tracing, like the natural thing about, especially when you have the trace, right? As soon as you discard the qubit, one application is just had this quantum state, right? Random, I would say mixed.
Mm-hmm.
If we discard it, what is left, right? We can just create a new state after that. That's like another application of discarding states. This is basically what in other software, quantum softwares, there's like those are represented usually as like a completely different abstraction from the quantum gates and quantum operators. It's like some kind of instruction one has to do when the circuit is being simulated. Okay, you want to discard your qubit here and create the same line, the different one in the same wire. This kind of instruction that you can only perform during the simulation. Oh, I don't know, maybe they have some better way of doing it, but that's how it seems like, right? But what is actually happening? You can apply this mixed effect of the zero information question, right? Effects, you can think of effects as just questions one asks about the state, right? And when the effect is just the inverse of the uniform mixture, it's basically some kind of stupid question without zero that has no information. So that's the same way of asking, of just discarding all the information altogether.
So it's kind of like saying if there's a quantum state of maybe a particle that's spin up and spin down, so it's in a superposition of spin up and spin down, but then you ask, is there a cat inside the particle? And then it's like, but once you ask that question, you destroy the quantum information, but you didn't get any kind of useful information. Your question wasn't answered because it's got nothing to do with cats. Maybe as a silly example.
Yeah. Oh, this kind of particular question is of something of sorts. I just instead of looking at the state at all, you just throw the coin, the fair 50% coin. It's just whatever this coin lands on, that's your answer, right? That's basically you just completely mix the state without even looking at it. I guess that's another way of looking at it, right? So that's what discarding represents, and this is just this composition of this uniform, mixed uniform effect, uniform mixture, right? So if I run this circuit, because I need to remove those echoes, that should be the same as sigma, right? So there's no trace of rho left anywhere. So that should be the same as sigma. Those are true. Yeah. And I even made the name for that. So instead of tracing it, I just have a named thing now. You can just reset and set whatever state you want. Just called reset. For some reason, it has no label, but it should have. It should call like reset. Maybe I'll come up with some nice diagram for it. I don't know how to render it.
Reset.
Yeah.
Okay, that's cool.
Okay.
Well, so just a question, with what we have here, would we be able to diagrammatically create as an example, the quantum eraser experiment, like simulate.
Oh, yeah, I guess so. It's like, I just look. No, it's not needed documentation, but it's like a raw documentation from without the compiled. It should look nicer. But I think we had some bunch of built-in circuits. Yeah. I don't remember where the eraser one, but I think we had some example in documentation about eraser.
Interesting.
Because he seems very interested in that one in particular.
Yeah, that one's kind of like the implications of it are potentially very profound, and then there's also some kind of debate about the validity of the outcomes, or rather the interpretation of the experiments. So some people are saying that it indicates that there's like time travel and that kind of stuff. So, and then other people are like, no, that's just the way it was done. You can't assume that. So the conclusions you drawn were like, so like it's quite an interesting experiment in terms of thinking about the implications and also the validity of drawing certain conclusions from the experimentation. So that's why that one's interesting.
Yeah. No, we do have. This is like a old documentation, but I think it's probably the intuition about this particular example can be expanded. But that's
Yes.
basically like the circuit representing the whole setup.
Hmm.
You can tell that it's old because it's like using some old colors.
Hmm.
We need to remediate all of those.
Yeah, I think there's been 3 or 4 different versions of this specific experiment where they've kept making it more and more complicated to try and like invalidate one of the original assumptions or conclusions.
Yeah.
So now it's like it's a whole long complicated thing now with like multiple multiple ways in which they're trying to check whether these things could actually travel, the information could travel backwards in time or not. What's the most complex quantum circuit that's built in, just as an example of how involved these things can get?
Well, some of them are parametric. You can depends on what argument it takes. It can be more complex. But you can, for example, actually there's some very primitive state preparation algorithm. For example, if you make a random pure state on 3 qubits, right? So that you can actually make a circuit that prepares the state from just a 0 register. And it kind of, for example, looks like this, maybe. It's a bunch of not very nice labels.
Mm-hmm.
Right? If it's gonna like if you're gonna try to create the similar thing for more qubits, it's gonna be larger, and it takes a while to create because it's not very good. To have some better ones. What else? For example, Fourier, very classic one, depending on how many qubits you want. Too big, it's not one. Right? That just creates a quantum Fourier transform. Oh, there's a bunch. Though I'm fan of like this kind of things that show one of those problematic circuits.
Yeah.
And about that actually describe some situation like those like eraser Bell inequalities.
When you say problematic, do you mean ones that present paradoxes?
Yeah, some kind of apparent paradoxes that people like to argue about.
Yeah. What's this one? Can you explain this one?
Yeah, let me remember. This is like the first kind of circuit one encounters in quantum computation, I think. It's like when you try to learn about quantum advantage, it's usually like presented, okay, this is like the simplest, seemingly advantageous algorithm that you can make. And I make it so it's like, okay, let me remember what it's all about. Right? So it's like there's some hidden oracle, right? It's like actually there is some random operator there, I like intentionally hide it from view so that
Okay.
to make it much clearer, right? And if you measure it, it outputs either. Let me do the probability plot. You measure in the x basis, so you either get plus, or I guess if it's really random, sometimes it's minus,
Wow.
right? So and it's depending on what you measure, that tells you about some property of this oracle. In that case, I think, let me just flatten it. It will just flatten all the subcircuits so that it actually expose the underlying gate. Right? Sometimes it's this, sometimes it's like nothing. I think there's like 4 alternatives that like you just choose from randomly, and because they represent 4 different Boolean functions with 2 inputs, right?
So is there a way to flatten that as well so you can see what's happening? In other words,
flatten what?
In other words, can we see? Is there a way to represent how it changes every time?
Let me just fetch because I have we had some actual page explaining this circuit in particular. Let me just find it really quick.
Which Jozsa. Richard, does Richard have any questions so far? Comments, questions? Okay, here's the Deutsch Jozsa algorithm.
Yeah, I'm gonna post the link in chat, right? So that's how it's set up. So there are 4 possible Boolean functions with 1 input, right? It can be either constant false, constant true, or it can reverse it or don't do anything. Just if it's true, it's true. It's false, it's false. Right. So there are 4 possible Boolean functions, and you can make 2 classes out of them. They're either constant, like this false or true, or they do something, right? And basically, the point of this algorithm is that you can distinguish them with a single measurement. Even though it's like if you don't know which function is the oracle, you have to perform at least like 2 queries of this oracle in order to determine which one it is. You kind of intuitively it makes sense, right? If this function that you don't know, it can return false. You don't know whether it's if your input is true and it returns false, you don't know whether it's always returns false or it just flips it, right? So you kind of have to make at least 2 classical queries. But quantumly, you just do this one measurement.
Ah, I see.
Right, and you can immediately determine, depending on whether your measurement is like x plus or x minus, you can determine whether your function was constant. I don't remember what's the second name for the non-constant one. There's some special name for that. Constant Boolean functions, balanced. Yeah, it's either constant or balanced.
Okay. But do you know which way around it is? Do you know whether it's not or identity? Or do you just know that it's either not or identity?
No, you don't know which one, but you can determine which class it is.
Okay, so that's
an example. Very useful.
Okay.
Yeah. It's kind of very contrived example, but it kind of works.
Okay, so that kind of sums up maybe, or let me ask that as a question rather, is that a way to sum up where quantum advantage could happen? Like that is an example of what a quantum advantage could be, but at the same time also shows the inadequacy of just having quantum advantage, sort of thing. Like it allows you to figure out stuff that in one measurement that would be impossible to do as one measurement classically, but at the same time,
I don't think like there's like a single thing like that when the quantum advantage arises, because it's still controversial what the actual resource of the quantum advantage is, right? So it's not that simple. It's just there's some bunch of different examples that you can show that this somehow advantageous in theory, even though it's still you can argue about it.
Okay, so take
But it's
out
not
the
just a
advantage
simple.
part. Yeah, so now it's not necessarily an advantage, but it's just an example of what quantum measurement can give you, which classical measurement couldn't in one step, something like that.
Yeah, it's basically all about the advantage is in practical terms is that you have to evaluate your query your quantum computer less than you would do the classical one, right?
Got it.
If it's like evaluates it with a certain time frequency that you can query as fast as modern classical ones, right? Under this assumption that it's like, or just in the purely theoretical sense, just count the number of times you do it without considering how actually fast those iterations are.
Okay.
Just like count the number of iterations of sorts.
Okay, so my question was, if you look at the output here at the bottom, where it's there's no connection, there's this connection, and then there's one thing on the bottom. Is there a way to represent all of those? Because that's kind of like pieces of this quantum circuit. Is there a way to represent the whole quantum circuit, or is the oracle kind of acting outside of the circuit?
Well, that was the whole circuit here, right?
Okay.
It's the whole setup, including the oracle.
Got it. Okay.
So you don't have what is the oracle is. It's one of those things, right? That encode those 4 possible Boolean functions. You don't know which oracle is, but that's how you set it up your quantum experiment and how you do the measurement in each basis, right? And then depending what outcome is, you can determine by the single measurement whether your function is constant or balanced.
Okay.
That's the algorithm.
Constant or balanced. Okay. Very cool. Okay, nice. Is there anything else that you wanted to cover? Maybe you mentioned that there were some interesting things you were recently thinking about in terms of what you want to do next, like potentially you wanted to work on like so like where to from here kind of thing. Like what are the next sort of things that you would like to have this framework be able to do, or that this framework has got you to think
There are
about?
there are multiple directions. So like this is one direction that I've just taken recently, but before I was having just a little sneak peek, because this kind of mixed operators allowed me to understand another interesting topic in quantum computation more. So I understood it a little bit more, just understanding those mixed operators. It's the measurement-based quantum computation, or one-way quantum computers. It's just like a sneak peek. There's like nice circuit here. Just and what's cool about it is that you see that this is the both boundary of the measurement. So those are the mixed way. So it's pre-traced measurement is how we did it here, right? You do the measurement, pre-trace it, because it's a mixed one. The outcome of this tracing also produces a mixed operator. That's how you show it. But now you can also control it classically. So it's like you can diagrammatically do the controlled measurement. So that's kind of a cool thing that basically will allow the framework to also express some hybrid computation in some way, just as a single diagram, because you essentially compute something depending on what your classical outcome is. Well, you're still going to compute some probabilities in the end when you perform the simulation by just constructing a bunch of tensors, but you can specify these classical operations of conditioning on the measurement result.
It's kind of like a logical gate, something like that.
Well, they all, even the conventional gates are kind of somehow like logical, like the controlled operations. Like this one gate is basically represents some quantum version of the Boolean function. Depending whether this wire is 1 and this is 0, then perform the X operator, X gate. If it's not 0 or 1, do nothing. Right? So it's kind of, but here you do it on top of the measurement. So diagrammatically it wasn't very straightforward to do without the pre-tracing of these measurement operators and representing them as this mixed maps, so that they like don't have any extra wires floating around, and they can just make these operators as a single direction circuit.
See, okay, that's cool.
So for example, like you can just talking briefly about this example of measurement-based quantum computing, what is actually things. What is this actually shows is this circuit above is the measurement-based version of this little circuit here. Just because this like has a single input, right? Single output or out here, but it computes the same thing as this like single qubit pre-operations over all, like a rotation of the qubit basically. So that kind of circuit can prepare a qubit into arbitrary state. You can think of those three angles as Euler angles in 3D, in 3 dimensions, right? You need like 3 angles to specify. Well, it's not really. Well, it's like a Euler angles. There's like even. Yeah, there's like a documentation here. So this is like 3 angles here is the same, almost the same as this 3. You can rotate this block vector into arbitrary direction by doing these 3 angles. But if you want to do it in the measurement-based approach, all you allowed is to make these 3 like consecutive steps. It's like the first step is you entangle a bunch of qubits together. That's what is called entanglement. So that represents a kind of resource that you can have in your system, right? Because usually entangled qubits represent some kind of resource that you can use. The more entanglement you have, the more operations you can perform. Let's say it's more advantageous it is. You can need, right? So the first thing in the measurement-based quantum computing, it should be MPQC, whatever. Right? You entangle a bunch of qubits, then you're allowed to make this a bunch of controlled measurements of those qubits, and then some correction. I don't know whether this correction is very useful or not. How to think of it yet, because I'm still learning. And then you just discard this bunch of auxiliary things and you get the same output.
I see. Okay.
Right? So instead of like firing some lasers, like usually in the quantum computation, if you like optics based or whatever, you fire, or neutral atom based, you fire some atoms, you fire some lasers to rotate your qubits by some angle, depending on how long is your pulse is, or whatever, right? Instead of doing that, if you already assume that you already have some prepared entanglement in some way, you just measure them in some angles instead. Right? So this shows, okay, this is the angle that you should measure it. So instead, this angles of phases of your laser, instead of you use them as your basis of your measurements, right? And the result of each measurement also tells you which next measurement is to perform. Like this shows you measure the first qubit with the 0 angle, and depending which you measure, like 0 or 1, you either measure the second one either with minus lambda or lambda. Right?
Got it. So that's the rotation that you're doing. So you're making measurements in a certain plane.
In a way, you can think you kind of mold this very general entangled state into whatever state you want. You want the state at the specific angle, right? But you just have this just very complicated entangled state instead. How do you mold this complicated state to this specific state with this in that direction? You need to like specify how to measure stuff in the specific angles. And that's how we do it. Right? This is like literally the example from Wikipedia that I've tried. Like this is a screenshot. So like, this is how this strings. This is like entanglement. This is the measurement. This is the correction part. That's how we do the circuit. So the next step would be to figure out how to make it more trivial. Maybe there's some general procedures, like not just this specific circuit, but given some arbitrary circuit, how do you convert it to this form? so that's a nice direction that we should follow in the framework.
Very cool. I like that. Can you touch on what this package can do that's not available anywhere else? So you mentioned there's this is often done in Python and sort of different stuff. These diagrams are really cool. Is this what's like a first that you were able to achieve here that's not available anywhere else?
Well, the immediate part is just usually those packages, libraries, and as I said, they're tailored towards software engineering and hardware, so they're all about qubits. But you can do arbitrary dimensions, right?
Oh, qubits being up or down, like a binary kind of.
Just two-dimensional binary states.
Oh, I get it. Now I get it. Okay.
So we can like make like random pure of 10 dimensionals.
Wow. Okay.
That's 10 qubits actually. That's 10-dimensional state.
Wow.
Right. And you can also put them in diagrams like this. Actually, if you do it, they're going to have this peak wire to indicate that the dimension is increased. Right, so that you can differentiate visually, but you can also show the actual dimensions. Like it's 10. Weird label. Psi. Do we have some circuits that naturally have some? Well, I can show you if you do the CHSH thing, there's some nice built-in operations that you can do with those circuits. For example, you can automatically convert them into phase space representation. This is another thing that our framework has, right? And so it's like visually almost nothing have changed. But actually, what actually changed in the phase space, those wires has doubled dimension, well, squared. If before it was two-dimensional, right? Now those wires in phase space, they're four-dimensional, right? What it means is that essentially you should think of those values on those wires not just as some complex amplitudes, but as quasi-probabilities or probabilities depending on what phase space basis you use. So any phase space representations are naturally probabilistic in nature. So no complex values involved. You just deal with real tensors, and every slice of the circuit represents some kind of probability distribution. And every gate is now some kind of stochastic process, maybe Bayesian one doing the backwards inference, but it's purely deterministic, purely probabilistic, no waviness with complex amplitudes involved. So that's another cool thing we have with the space representations. And it's basically allowed by this like flexibility of dimensions and bases. That's what allows us to do this, so that we can explore all these different representations.
I see.
Different forms of computations too. It's like and because we like work for Wolfram, we also like trying to while I'm working on this framework, I always try to draw some connections to the Wolfram physics project and all that. It's like draw some wild graphs. It's like I don't remember how it works, but I have some experimental ones, like a quantum circuit multiway path graph, multiway graph. Let's try it. I don't remember how it works. Like this is already like a built-in phase space version, which is a little bit smaller. There's like pre-contracted, but this like a Wigner is the guy who is known for the Wigner distribution and phase space. This is like a Wigner CHSH version in phase space with some pre-measurement and I think this should compute maybe. Need some time, but it works.
Yeah, I was about to say that seems like it's going to be a complicated thing to perform.
Yeah, this is supposed to return if it works as some kind of discrete version of the Feynman path integral.
Wow.
But instead it's just it's a sum representing how your probabilities flow, quasi-probabilities, because we are directly operating on the probabilistic phase space version of the circuit. It's going to show not how amplitudes flow from your initial state to the all possible possibilities and of the output. It's going to show just the quasi-probabilities instead.
Hmm.
I don't know. It'll take a while.
Is it, and I saw there were some multi-way graphs there, and specifically in terms of potential applications in the Wolfram Physics project. What was your thinking in terms of how this could inform work on that project?
Well, I've been thinking about how, well, I personally think like this probabilistic connection is very useful because that would allow more natural, no, something broke. Yeah, I haven't used this function in a while. I need to revisit it. But I think I have some pictures. Hold on. Well, maybe that's one. Is it here? Do I have some graphs? Well, that's the multi-way graph.
Okay.
Do I have some path graph in here? I don't think so. But anyway, like this multi-way graph, for example, takes the circuit. In this case, I think it's taking this circuit and tries to apply gate after gate in this multi-way fashion, like the multi-way system. I wouldn't like draw the connection of this particular representation to physics project. It's just a toy example of multi-way systems within the quantum theory, but without connection. It's like not even, you just treat gates as some kind of rules that you apply. And as soon as there is entanglement created, you represent it as branching, right? So it's more like very straightforward way of doing of extracting the multi-way system from the circuit. You just apply gate after gate. You track the state that you currently have. If it's separable, then it's a pure state. You don't branch. But as soon as the entanglement created and there's no way longer to represent the state as a tensor product, you branch and you also weight each label with the corresponding probability, and you just do it for all the gates in sequence, right? Within each new branch, so that you kind of can represent. So it's still kind of like a path integral version, so that in order, for example, to extract the probabilities of the final outcome, the output of the circuit, you just have to like sum up all the possible ones at the end, right? So it's like just sum all the final states. There are some probabilities corresponding to each of those, and you get the final. Just in the path integral, you would actually solve the paths instead, not just take the sinks of this graphs, the vertices at the end, the leaves, but actually sum up the paths and the probabilities along them.
Okay.
Maybe I can. Some small example. No, that's a good example.
Okay.
Small circuit works, right?
Okay.
It kind of shows you how the state evolves with each of, because they just two gates there. You started with nothing. Actually, it's the same as applying the register. You created the register state by default, right? And then you apply the Hadamard, right? It's here. How's it work? Well, it's clear that the final state representing the ball state, right? So that's the superposition. But you kind of either do this or that. Yeah, well, the Hadamard is either makes a 0 or 1, so that's why I split.
Okay, and then once there's a 0 or 1, then it constrains the potential possibilities of each of those to only either be a 0 or 1 for the second qubit. something like that.
Yeah. And I remember that also the color of the edges also represents the actual probability.
I see.
So that sometimes it can even do, well, if it's in phase space. I think that's
Okay,
the deal. If you do the phase space version of it, if there is a blue edge, I think that means it's a negative quasi-probability. Because in general, there's some negative values in there.
Negative quasi-probability.
Yeah. Well, let me show you one cool graph that every state have. So remember that we have can create a random arbitrary quantum state, right? Which is just a density matrix. But it's a cool representation that we have. It's called transition graph. Not exactly this one, but this one, which is much simpler. This is just means that this is like a separate method for when the dimension is prime. Okay, so because 2 is prime, that's for the qubits.
Okay.
Let me label the edges with the weight. Okay, so that's representation of the state as a transition graph, meaning it's a representation, meaning that it's one-to-one corresponds to the arbitrary density matrix to this kind of weighted graph, right? What are the meaning of those individual things on the graph? Vertices are red vertices are the basis states of your computational basis, right? And the blue vertices are the basis states of the X basis, which is the conjugate, the conjugate version of the red ones. It's like in the classical phase space that would correspond to position, and that would correspond to momentum. But this is just a two-dimensional version of those. Coordinate and the momentum, right? Two-dimensional version of those. Or you can think of those different irritations of spin or something, like spin and phase, whatever. Any conjugate variable, which are connected by some Fourier transform, right? And the edges are the probability transitions from one vertex to another. And there are kind of weird ways that you can compute probabilities of measuring this state in this graph. For example, let's give it a name again, right? You kind of, for example, if I ask for probability of that state, which in this case is just your trace of your diagonal of your density matrix, right? That's how we compute the probabilities. If you're given a density matrix, this is the probabilities of measuring this state in the computational basis, right? In order to extract this particular probabilities from this transition graph, there's some nice way of doing it. Is just basically treat those weights on the edges as some kind of flow of probability. So in order to compute probability of measuring 0, you compute all the weights that come into that vertex and subtract all coming out. In this case, there's no edges coming out, but in general there will be. Actually, let me try to find the one that has negative value in it. Oh, there, right? There's a way. I have this additional option that just if you have that just gonna turn every negative edges into positive ones and reverse the direction. So basically, all the information is still there, right? It's still the same graph. Well, to kind of swap 0 and 1, but basically reverse this blue arrow, right? So that contains the same information as here. It's just now this one state has the one incoming edge and one outgoing edge.
Interesting. Oh, okay.
And if you want to compute the probability of measuring this one, like this value, you should basically subtract this one from this one.
Yes. Okay.
See? Like for example, to measure the probability of 0, you sum up these values because they're all incoming, right? So that's but you also can recover the whole density matrix for this from just this edge weights, right? So it's one-to-one correspondence. You can think of the state at some your conventional density matrix with complex values, but you can also think of this weird transition graph between those two conjugate basis elements, basis states.
Makes sense.
And then, like, if you take an arbitrary quantum operation, a quantum process that acts on this state, that's just gonna manipulate those H weights in some way, right? So just and you can, in theory, you can. It's not maybe not very practical, but in theory, you can formulate the whole of quantum theory in these probabilistic terms, like using this kind of graph, transition graph representation, or I can show you a different probabilistic representation of quantum state, but there are several. But you don't have to touch like complex amplitude at all.
Yes. We mentioned that previously when we were explaining this. Yeah.
For example, like another related thing, I think it's the same kind of. Is it the same values? I think those are the same values. See, you can form this table. That's basically your phase space grid, right? So you can make this table because it makes sense to actually assign. Let me do it quickly. Names. This is rows or columns. It's the other way around, right? So you can make. So this is like your phase space grid. If you have more dimensions, the grid's gonna grow, and it's like in the limit of infinite dimension, you have this continuous phase space when you have a your coordinate versus momentum, just like every point, but it's in probabilistic in a way, and in this case even quasi-probabilistic, so that each point is actually weighted by some quasi-probability. And the way you extract naturally those probabilities, for example, from the phase space quasi-probabilities, you marginalize over the conjugate variable. So in this case, you have to sum up the rows of this column, right? So naturally you get the same kind of computation that adding weights in this graph. You sum all the rows of this grid and you get the same probabilities as here. If you want the probabilities in X basis, in the momentum basis, right? You can convert the state into this basis, and now you measure it, kinda, and you get different probabilities. Those correspond to summing up the columns. You get the same numbers. You sum up you marginalize over computational basis now, and you sum up the columns.
So would that be like saying we know exactly now where the position is, but we have a probability in terms of momentum? Something like that.
No, that's how you in conventional probability theory, if you have two variables, joint distribution, like P of Q and P or something, right? Coordinate versus momentum. How would you turn this into probability of Q? You marginalize it. You basically compute the sum over all the P's of the joint probability. Right? That's the same way what you're doing here. You have this table, which is your P probability of coordinate and momentum. You want to just compute this probability, you sum over all the possible momentum.
Okay.
Because you don't know which one it is. It's kind of, right? Purely in probabilistic terms, you have random variables. They have some joint distribution. In this particular basis, there has to be negative sometimes. But there are, so we have this nice phase space transform. You can actually transform. We have a very many different bases of phase space. Right? For example, this cubism, which is all about probabilistic representation of the quantum theory, when you represent all your states and operations in the Bayesian terms and all that. They have some very technical way of assigning a very specific basis in every dimension. They have like, they still don't know how to compute it actually in arbitrary dimension when it exists. It's not yet proven, but there's some numerical evidence that it exists in every dimension. You can find this very specific nice basis. So that's in a way there's like some nice basis or maybe up to some rotation in every dimension that makes sense to assign to every state those particular outcomes. What I mean is that if you convert, because you convert, now you have a representation of the state in the phase space. Now your amplitudes act as probabilities instead, right?
Okay.
So if you sum them up, you always get one. So that's a distribution. And choosing the basis in the phase space basically means coming up with the nice basis elements in which you can measure your state. If you determine those probabilities, you determine the state completely. So you basically extract the full complete information about the state by measuring this specific basis. But this basis is like has some other nice properties, meaning that it's like informationally complete. It's like there's no quasi probabilities. Like they're always going to be positive, right? It just maybe loses this nice marginal property so that you can like sum up rows and columns and extract probabilities that correspond to the actual values in your experiment, right? But they're still connected to those by some kind of procedure, some inference. So yeah, you still can do some inference and extract the actual probabilities of the measurement results in whatever basis you want. But this is like would represent the most natural basis of the state in some sense.
Very cool. Okay. Anything else you just wanted to squeeze in for this session, or is that enough information for a 2-hour stream?
I don't know. It depends. Maybe you have some more questions.
Yeah, just more maybe general kind of like philosophical questions just around quantum mechanics itself. I mean, what we're doing here, would this be classified as quantum mechanics, like as a broad scientific endeavor? Like,
no, I wouldn't call it quantum mechanics. Just quantum information or quantum computation is better. Quantum mechanics is usually referring to like continuous case when you have actual continuous variables of a coordinate and momentum, when you have momentum represented as a differential operator and you have continuous Fourier transforms. Right?
Okay, so more specific in the world of physics. So quantum mechanics is like the laws of physics, but the quantum version of that. Whereas this is just like the idea of quantum states, quantum information, and then are these two different branches of what would be the higher level thing that we're discussing, or does all of this fit under quantum physics?
Well, in a way, yes. Just you can always, in principle, take a limit. Like this represents the quantum theory in its discrete form, but you can, in principle, take the limit into continuous one and extract the quantum mechanics if you want to, right? And there's even formulations purely in this finite, countable, dimensional sense even of the quantum mechanics itself. It makes much more convenient to operate in the continuous like framework rather than finite in some cases. But when you deal with the quantum computation and quantum computers, they define that discrete cases.
Discretely. Makes sense. Okay. So there's kind of the natural world where there's observations in space, for example, where quantum mechanics, you kind of, it's better to think of things in the continuous case, but when it comes to quantum computation and like maybe building quantum computers or doing that sort of thing, then you would have to think in terms of the discrete way of doing things. So this quantum framework allows you to work with these ideas and create circuits for the discrete case, and then what you're saying is at the limit you can think of how this can get you to the continuous case as well, potentially.
Yeah.
Okay.
It's not like I had some ideas of how would one naturally represent the continuous variables in our framework too, and it would require some work, but you can imagine that there's just another modification of the quantum basis. It's like we have like quantum basis, which some explicit like finite dimensional, like integer dimensional things in there, but you can somehow squint a little bit, and because you can even allow like one-dimensional things, like this is a one-dimensional quantum state, right? Just with some arbitrary symbol in it as a single amplitude. But you can somehow think of this state as basically continuous, so that you can kind of hack around it and pretend that this variable represents how we would quantify all possible infinite dimensional states. Right? Okay, if this is like a coherent state, which is very famous state when you try to represent like a state of the photons in the laser or whatever, right? It's quantified by a single number, right? So that it represents this Poisson distribution of the number of photons or whatever. This is just a single complex number, and that can be this complex number. But if you treat this state, even though it's finite dimensional, represented as a one-dimensional discrete state, but your amplitude is can be just symbolic thing, and you would need to replace all your inner products when you're doing the dot products. When you're doing like the dot product with those tensors in our framework, the amplitudes are being just multiplied together. But if it's like there's some information in the basis that we know that this one-dimensional basis is actually contains the infinite amplitude in a way, instead of just multiplying them, you have to integrate it. Right? So you just replace all the inner products with some integrals, and you can hack around because we have the Wolfram language that knows about symbols and knows how to integrate symbolically. We can potentially represent even infinite dimensional systems, and even combined one. You can have like infinite boson, even dimensional boson state, like a Fock state. And then when you inner product is an infinite sum and some fermion, which is just qubit, if you squint, right? And you can entangle them together, whatever. Right, so it's like one potential direction we can also explore, just trying to encode those hybrid systems with infinite and finite dimensional subsystems.
Very nice.
Interacting with each other.
I like the analogy of being able to go from discrete to continuous as the act of just squinting a little bit. It kind of makes sense. If you do this, then the discrete becomes continuous. Yeah, that's very cool. And I think what's also cool with this, just from you going through this in a little bit of detail, is the ability for someone that might be intimidated with engaging with quantum theory to say like, look, there's actually code that you can run in a notebook that lets you work with these things and calculate the probabilities or actually experiment with it, instead of just, reading a bunch of theory and then trying to work with it by writing out equations or learning the equations and then calculate if the equations are correct. You can literally just open up a notebook and start working with this stuff as code. So this is a great way for software developers or people that are good with writing code to start getting involved in the world of physics. That's very cool.
Yeah.
Cool. What does this QR code do?
Oh, that's for this particular notebook.
Okay.
If people are interested.
Nice.
So I posted the link there so people can download it and just follow through this exploration that we did today.
Great. Yeah. Okay, that was really cool. Appreciate your time. Thanks for working through this. Yeah, we can make a little post about this potentially, just so people can understand that it's a nice kind of like full session on a lot of the value of this quantum framework. Great. Okay. Cool. Yeah, so for anyone that's interested, we'll post this notebook here. There's the cloud version, so that means you don't need to have Mathematica installed. You can literally just click the link and go look at the notebook in your browser. And yeah, maybe what we can do for this notebook, in case someone finds it there, we can paste the video link in this notebook, so you can get it. You can follow along both ways. And that's how you install the packlet there.
Yeah. So now it's going to be functional.
Cool. Is that going to be the same link?
Yeah.
Okay. Updated. Great. Okay. Thanks so much. Thanks everyone for tuning in, and for the audience members in the chat who stuck with us talking about quantum theory for 2 hours. Well done. Okay, all the best, and we'll chat soon. Tomorrow we're going to do a live stream, which will be a live science stream, and Thursday we're going to do another live science stream. So we're going to do infogeometry and observer theory in that order. So rebooting some ideas in observer theory and trying to make some technical advances in that world, and discussing potentially how much there's still to be done there. So yeah, tune in for those 2 streams as well. Otherwise, all the best, and we'll catch